We've investigated some of the rules for differentiating functions, but in order to use those, we need to know how to differentiate basic functions like exponentials, logarithms, trig functions, and so on. Let's begin by looking at how to differentiate exponentials and logarithms and functions of those. So we'll start with one thing that you probably know already, which is a derivative of e to the x is e to the x. It's the only non-zero function which has its own derivative. But where does that come from? In order to work this out, let's start with a general exponent. Let's consider a to the power x, where a is a positive number. So we start with using the definition of the derivative, the limit as h tends to 0 of a to the x plus h minus a to the x, all over h. Now what we need to do is simplify that. So we can simplify this using the rules of exponents. And what we notice is that the a to the x doesn't depend on h. We're taking the limit as h tends to 0. So the fact that it doesn't depend on it, a to the x, means that we can take it outside the limit. Now what we notice is that the limit that's left is actually the derivative of the function at x equals 0. So what we've shown then is that the derivative of this function a to the x is equal to a to the x times the derivative of the function at x equals 0. So where does the number e come into this? Well, the number e is defined to be the number such that this limit is equal to 1. So for this special number, this limit of e to the h minus 1 over h, as h tends to 0 is equal to 1. So just to be clear, as h is tending to 0, the numerator is tending to 0 and the denominator is tending to 0. So we have a limit of the form 0 over 0. We'll come back to these sorts of limits later in the course, but for now note that it's not a trivial statement to make. So given this then, we have shown that for this special number, d by dx of e to the x is just e to the x. Another way to think about this is if we look at the graph of e to the x, the slope as it crosses x equals 0 is equal to 1. What about for a to the x? So using the laws of logarithms and exponents, let's write a as equal to e to the log a. Then we have a to the x is e to the log a times x. So now using the chain rule, we have derivative of the exponential part times the derivative of log a times x. Now that's just a constant times x, so therefore this is equal to e to the log a times x times log a, which is just a to the x times the logarithm of a. So that's pretty neat. Now using the chain rule in general, the derivative of the exponential of a function is the exponential of the function times the derivative of that function. So that's all good for the exponential, but what about logarithms? For this we need to use a little trick called implicit differentiation, which we're going to come back to later. So let's let y equals log x. What we want to find is the derivative of y. How do we find that? Well, here's a trick. If I write x equals e to the y, I know how to differentiate e to the y. I know how to differentiate x. So if I take derivatives of both sides, then that implies that 1 is equal to e to the y times y prime. And rearranging, y prime is 1 over e to the y. And we know that e to the y is equal to x. That implies that d by dx of y, which is just log x, 1 over x. So that's a very neat trick for finding derivative of a function that we didn't know how to do before. In general, it's worth noting that the derivative of log of the absolute value of x equal to 1 over x, whether x is positive or negative. This is a really useful result we'll come back to when we look at integration. For now though, you could have a go at proving it. Armed with the derivative of the basic log function, we can now differentiate logs of functions. So if I'm differentiating the logarithm of a function u of x, then this is 1 over u times du by dx. Is there anything else we can do with logs and exponentials to find derivatives? Well, it turns out there is. How do we find derivatives of things like x to the power x? Turns out there's another neat trick we can use now that we know how to take derivatives of logs of functions, and this is known as logarithmic differentiation. Let's try rederiving the power rule using logs. Previously we've only proven this actually for n equals an integer, But by using logarithmic differentiation, we can prove it for any value of n. How do we do this? Well, let's take logarithms of both sides and then use the law of logs to simplify it. Now, if I differentiate both sides of this, remembering that y is a function of x, okay, so remembering that y is a function of x, the derivative of log y is y prime over y, which implies dy by dx is n over x times y, which is x to the n, which implies then if I resubstitute for y, d by dx, x to the n is nx to the n minus 1. Now what's happened there seems like a little bit of magic. So what we've done is we've taken logarithms of both sides of our equation and used the law of logarithms to simplify it. Then we differentiate it, then we rearrange for y prime, then we resubstitute for y wherever it appears, and hey presto, we've found our answer. This can be used in general for much more complicated examples. So let's find the derivative of x to the x to see how this works. We start step 1, take logs. Log y is log x to the x, which simplifies to x log x. And by taking logarithms, we've turned a power into a product. Power now becomes a product. So when we differentiate it, we can just use the product rule. This implies if we take derivatives d by dx, we have y prime over y. We differentiate using the product rule, so let's differentiate the x first, leaving log x, plus x times the derivative of log, which is 1 over x. So this is 1 plus log x. This implies y prime, which is the answer that we're after. In general, we can find the derivative of x to any function of x using this rule of logarithmic differentiation. And in fact, it's relatively straightforward to derive the following formula. So you can have a go at deriving that.